Hi, I'm Zor. Welcome to Unizor Education. Today I would like to talk about one particular operation on the vectors. It's called scalar product. Yes, scalar product. Yes. Well, we operate with different objects in mathematics. With numbers, we can add or multiply them, for instance. With triangles, for instance, we can calculate their area or something like this. So basically, vectors are also subject of manipulation. We know how to multiply a vector by a constant. We know how to add two vectors together in both coordinate form, the tuple representation, and in geometric form when basically we know the lengths and the direction of the vectors. Now in the first case, for instance, direction remains exactly the same and the length is multiplied by k. If k is positive, the direction is the same. If k is negative, direction changes the opposite. Now if you are summing together two vectors, then we are using this rule of parallelogram, which is the result. Now, in coordinate form, if you remember, if A is in two-dimensional case represented as A1, A2, and B is represented as B1, B2, their coordinates, x coordinate and y coordinate of the endpoint of the vector. Then multiplication by a constant means actual multiplication of each component, because that actually gives you the proper lengths without changing the direction. And in case of addition, you just add correspondingly x and y coordinates. So the sum would be a1 plus b1 as an x coordinate and a2 plus b2 as y coordinate. In three-dimensional case, it's the same. Now, these are old operations which we have learned. Now, this lecture is dedicated to a new operation, completely new operation, which we can perform with vectors. Vectors actually came from physical representation of certain objects, like speed, for instance. And scalar product also has certain physical meaning, which we will address later on. So right now, let's just concentrate on an abstract operation on two vectors. And let's try to examine it first in tuple representation in the coordinate form, and later on, next lecture will be dedicated to their geometric representation. So let's say we have two vectors. In their coordinate representation, in their tuple representation, okay? Now, I have chosen two-dimensional case. Later on, I will explain the three-dimensional, it's exactly the same. So it's just easier to manipulate this two-dimensional case. What is this operation? Well, we know the arguments, two arguments. Now, if we add, for instance, two vectors, we get the vector. If we multiply a vector by a constant, we get a vector. If we do this operation, which is called scalar product, or dot product, or sometimes inner product, as a result, we get the real number. So this operation, if you want, we can use the symbolics of the function. If the function of two vectors, its result is some kind of a real number. Now, well, that's fine. I mean, we can obviously define many different ways we can derive the real number from these two vectors. For instance, well, we can add their lengths together. Is that okay? Fine, it's a function. You calculate the length of the first one, the length of the second one, and you add them together, or you multiply them together. Well, this is a different operation, and it has certain physical meaning, as we will discuss later on, and that's why I would like to define this operation not as just the formula. I mean, I can give you the formula right now if you want to. The dot is the symbolic representation of this scalar or dot product. Using the formula, it's this one. In two-dimensional case. In three-dimensional case, I add the third coordinate. I multiply, I'm sorry, my mistake. In three-dimensional case, it would be A3, B3, etc. Now, I can give you this formula, and then we can examine the properties of this particular scalar product, this particular real number, which is a function of these two vectors. But that's not really interesting. I would like to approach this in almost like axiomatic methods. I would like to think about this function as having certain properties, and then derive this formula based on these natural and reasonable properties which we would like to put into this. Now, why am I going to do this? Well, primarily because this course is not about giving you some facts about mathematics. It's about to develop your creativity and analytical thinking and logic. So that's why I would like to put some foundation, the logical foundation for this particular operation first, and then derive the formula from these seemingly logical and seemingly reasonable assumptions. Almost like axioms, if you wish. So what are these assumptions about the function of two vectors which results in some real number? Well, let's think about it. I have actually put something for myself as a guiding point. So number one, rule number one, I call it independence of coordinates. Now, you see that these are coordinate representation, right? Now, if we change coordinate in some way, in some good way, so it doesn't change the lengths or angles, for instance, we can rotate our coordinate system. From this system, we can go to this system. We just rotate it. Well, obviously, all the coordinates of all the points will be different. And obviously, the vectors also will have different coordinates. However, what will remain in this rotation? Well, the lengths of the vectors, for instance, will remain, and the relative position of two vectors. Let's say I have one vector and another vector. No matter how I move the coordinate, the relative position of these vectors, which is actually an angle between them, is the same. So, my point is that whatever calculation with coordinates we make, the result of this calculation should not depend on something like rotation or maybe shift or whatever. So whatever the transformation is done, which doesn't really change the fundamental properties of the vectors, which is their lengths and their relative direction, which is angle between them, if it's not changed by change of the coordinate, then the result of the scalar product should be the same. So it's a function of vectors' physical properties, like lengths and angle between them, not the result of their concrete representation in a concrete coordinate system. So independence of the coordinate system is very, very important. It's property of the vectors and their physical essence rather than their concrete representation in some coordinate system. So that's number one, property, independence of the coordinate system. So the function which operates with these A1, A2, B1 and B2 should not really change the result if we change coordinates in a nice way. Rule number one. Okay, now number two. Rule number two I can express this way. This is 0. Now, what is 0 with the bar on the top? Well, it's a null vector. Null vector has 0 lengths, by definition, right? So it doesn't have really a direction, it has 0 lengths. Now, I think it's very reasonable to expect that our scalar product of any vector with the null vector will result in a real number 0. I think it's very reasonable and very logical assumption. Rule number 3. Now, this is a unit vector, the vector which has a unit length. Now, I think again it's reasonable to assume that if you have if you have the same vector multiplied by itself, and the vector has the length equals to 0, so it's not two different vectors, it's actually vectors which are the same. We repeat it, we multiply it by itself. Then the result must be 1. I think it's very reasonable to expect that the vector of the length 1 multiplied by itself using this scalar product should give the result of this operation should be equal to 1. I think it's reasonable. Commutative property. Again, very reasonable property. So the formula should be symmetrical relative to A and B. If we change their order, the result would be the same. Now, we always expect something like a product, whether it's a scalar product or a product of different numbers, to be commutative. And also, there is a associative law with multiplication of one of the vectors by a constant. So if you multiply one of the vectors by a constant and then multiply by another vector using the scalar product, by the way, pay attention, this is a product of a vector by a real number. This is a scalar product of two vectors, this one and this one. I'm using the same dot because all the properties are really exactly the same, like commutative law, multiplication, the associative law of multiplication, and distributive will be as well. That's the next one. So anyway, this should be equal to k multiplied by scalar product of A and B. So this is kind of an associative law, but in this case we are mixing two different multiplications. This is scalar product, this is a product of the vector by a constant. This is scalar product, result is a real number, right? So this is a multiplication of two real numbers. Anyway, I'm using the same dot because that's how mathematicians are using these in these cases, and I'm not going to invent anything else, but you should really understand the difference between this dot and this dot and this dot. They're all different. This is scalar product again. This is multiplication vector by a constant. This is scalar product again, and this is multiplication of two real numbers. That's why I put the parentheses. And, well, obviously, with multiplication of another, it's also the same thing. If I multiply by a constant another component of this scalar product. All right, and the next one is distributive law. Sum of two vectors, this is a vector, scalar product with the third vector equals to the first component of the sum, scalar product with the third one, then the second component of the sum multiply and then add it together. So this is a true distributive law. So basically the laws of scalar product are very natural as far as I understand. Maybe the law of independence, the first one, might present certain problems, but in general there is nothing wrong with asking that the product of two vectors depends only on their physical characteristics like lengths and direction from one to another rather than the coordinate system. So I think it's natural, and as far as these guys are concerned, that anything multiplied by null vector gives 0 and unit vector by itself multiplied will give 1. I think it's also quite natural, and it corresponds to your and mine understanding of what actually the multiplication is, right? Multiplication by 0 should give 0, and multiplication of 1 by 1 should give 1. Now, so, being as it may, I think it's sufficient number of rules or axioms, if you wish, to derive the formula for scalar product of two vectors in the coordinate form. And that's what I'm going to do. Now, what I will do first is the following. Think about the vector A, which has components A1 and A2 along the coordinates. I can actually write this vector as the following. As a constant A1 multiplied by a vector 1, 0 plus constant A2 multiplied by a vector 0, 1. Now, why? I think it's quite obvious. If this is the vector, this is your vector A. X component, Y component. Now, this piece is A1, this piece is A2. Now, obviously, vector, this one, equals to sum of this vector plus this vector, because that's how the addition of the vectors is defined. This is the rule of the parallelogram. In this case, it's actually a rectangle. Now, what is this vector? It has a length of A1, right? And it's directed exactly the same way as this vector. This is number 1. So the vector from 0 to 1 has coordinates 1, 0, right? Now, the vector from 0 to this point is exactly A1 times longer than the unit vector along the x-axis. So that's why I specified this vector as A1 times the vector A1, 1, 0. Similarly here, unit vector is here. This is number 1. And this vector is A2 times longer than the unit vector along the y-axis, which is 0, 1. So if I add these two vectors together, I will get my vector A. Now similarly, this is equal to B1 times 1, 0 plus B2 times 0, 1. So these are vectors in the parentheses in their tuple representation. It's like this one is a tuple representation. So these are unit vectors. 1, 0 is a unit vector along the x-axis, 0, 1 is unit vector along the y-axis, and A1, A2, B1, and B2 are real numbers. So this is a true representation of vector A as the sum of two vectors along two coordinates, x and y. Now, let's multiply that. Now, one vector is a sum of two vectors, and another vector is a sum of two vectors. So I can use these laws, very reasonable laws, which we have agreed with, of commutative and distributive laws and associative laws, whatever, to multiply sum of two vectors by sum of two vectors, right? Now, what will that be? Well, if you multiply these vectors, you basically open the parentheses in exactly the same way as you open the parentheses when you multiply sum of two numbers by sum of two numbers. So it's first times first, first times second, second times first, and second times second, right? Because that's how you multiply using the distributive law. So what if we will do this? All right. Let me put this aside. All these rules I have already specified. I don't need this picture either. So the multiplication would be as follows. A times B equals A1 times vector 1, 0 times B1 times 1, 0. That's first by first. Now, let's again think about what are these dots represent. Well, this is a multiplication of a vector by a constant. This is multiplication of a vector by a constant. And this is the scalar product, because the result of this is a vector, the result of this is a vector. Plus, first by second would be something similar. So the first one is this times this. Now second by first, that's A2 times 0, 1 times B1 times 1, 0 plus A2 times 0, 1 times B2 times 0, 1. All right? Now, using one of the rules which I have already specified, like multiplication of one of the vectors by a constant actually is the same as you multiply the vector by itself to the second component, and then the result will be a constant. And then I will repeat exactly the same thing the second time. So instead of this, I can use, well, let me put it on the right, and then I will wipe out. So it would be A1, B1, and then 1, 0 multiplied by 1, 0. That's what it will be. So I factored out, basically, I took out the A1 outside of the scalar product and then B1 outside of scalar product. I twice applied the same rule. So I will replace this with this. Now, similarly, I will replace this with A1, B2, and then scalar product of 1, 0 by 0, 1. That would be instead of this component. Instead of this component, I will have A2, B1, 0, 1, scalar product 1, 0. And finally, this one would be replaced with this. Scalar product 0, 1. And this is sum. All of them. Okay. So that's our scalar product represented in this particular form. Now, what is this? Well, it's a unit vector, a unit of length of 1, multiplied by itself, and one of the rules is, if you remember, unit vector multiplied by itself should give the result of 1, right? So instead of this, I can specify this. And that's it. Because the scalar product of 1, 0 by 1, 0 is equal to 1. Same thing with this. This is the unit vector along the y-axis, which is also multiplied by itself as a scalar product will give 1. So instead of this, I can put this. Now, these guys are a little bit more complex. These are two vectors. They are also unit vectors, but they are not the same unit vector. It's two different unit vectors. And actually, they are perpendicular to each other, right? 1, 0 is here, and 0, 1 is here. One is x-axis, another is along the y-axis. So they are perpendicular to each other. So I cannot use this particular rule of unit vectors multiplied by itself equals to 1, because it's not by itself, it's two different unit vectors. Okay. But let me point out, first of all, that these two are the same because they are commutative, right? 1, 0, 0, 1, 0, 1, 1, 0. So whatever the result of this multiplication, it's the same in these two cases. So what is the result of this multiplication? Well, let's just think about what is 1, 0 times 0, 1. Just this particular what is a scalar product of this? Okay. One of the first rules was independence of the scalar product of the coordinate system. Which means if I take two vectors perpendicular to each other and do the scalar product, the result of this scalar product should not really depend on whether I turn my system of coordinates or I maybe reflect it relative to some. So I perform certain changes of the coordinate system without really changing the lengths or the angles, right? So let's consider a different case. Let's consider this case. Minus 1, 1, 0. It's this one. It's 0, minus 1. Now, let's compare this pair, this pair and this pair. Well, in both cases, the lengths of the vectors are 1. In both cases, the angle between them is 90 degrees, the right angle. So, according to my rules of independence of the scalar product of the coordinate system, no matter how you do this scalar product, it should actually be the same. Why? Again, because the lengths of these two is equal to 1 and 1, and the angle between them is 90 degrees. The lengths of these two are 1 and 1, and the angle between them is 90 degrees. So the scalar product should be equal, right? But now, let's think about it. What is this? I can have this minus 1 as a constant times 1. Right? And according to the associative law of multiplication by a constant, I can take this constant out as a constant, and then have 0, 1, 1, 0. So this is a scalar product, and this is multiplication by a constant. And what do we see? Look at this. This and this. This is the same, right? So we have something like x equals to minus x, right? Where x is the scalar product of this. So what is x in this case? Obviously x is equal to 0, right? That's the solution to this equation. So my point is that multiplication of two unit vectors, the scalar multiplication, scalar product of two vectors of the unit lengths perpendicular to each other, the result is 0. So there are no other components in this sum. They are all equal to 0, and only the first and the fourth one remain. So I have derived the formula like this. I'm not giving you as a definition of the scalar product in the coordinate form. Because again, you might actually think about why. Why is this particular formula and not something like, I don't know, A1, B1, A2, B2? This is also a real function of all four coordinates, right? But it's not this one, it's this one, this particular expression, which is actually an expression which satisfies all these reasonable, as I'm considering them, rules which I have specified in the very beginning. And one of the very important rule is an independence of the coordinate system. So what I want to say right now is that if I will change the coordinate system, I will, let's say, rotate it. I will change it in a way which does not change the length and the angle between two vectors. If I rotate up the coordinate system, the vectors basically have the same lengths and the same angle between them. Then formula would be different, but the result would be the same. Coordinates will be different, but the result will be the same. That's very, very important to understand. Okay. Now, obviously, if I will change the coordinate system in a way which is like stretching, for instance, when the length of the vectors is changing, then all bets are off, obviously. This is not a transformation of the coordinate system which we are talking about. We are talking only about the transformation of the coordinate system, which does not change the matrix of the space, does not change the lengths, the angles. These, by the way, are called orthogonal transformations of the coordinate system. And rotation is one of them. Symmetrical reflection relative to, let's say, y-axis would be exactly the same. And some others. All right. So that's what I wanted to present to you today. This formula, which again is not a definition, I derived this formula using some logic and well, basically we have created a new operation called scalar product based on certain reasonable principles which we put in the beginning. And that's very important because how mathematicians actually came up to this formula. They didn't come up just from the blue. They were thinking about, we need a formula which would reflect certain properties which we would like to preserve, like, for instance, independence of the coordinate system transformation, distributive law, associative law, multiplication by a number, etc., etc. And then they logically derive this particular formula. So that's what I would like to inculcate in your minds. All these formulas are not just given to us by God or something like this. We have come up with these formulas as a result of logical conclusions based on certain principles which we consider reasonable. We can actually take them as axioms. Okay, so this is a representation in the coordinate form. And again, let me point out, if I will change the coordinate system in an orthogonal form, so it doesn't change the matrix, then obviously the coordinates will be different of these two vectors, right? But the result of this formula calculation would be exactly the same number. So the scalar product is invariant, so to speak. It does not change with relative to orthogonal transformation of the coordinate system. Okay, that's it for today. I do suggest you to go through notes to this lecture on unizor.com. And the next lecture will be about geometrical representation of the scalar product. Thanks very much and good luck. Hi, I'm Zor. Welcome to Unizor Education. I will continue talking about scalar product of two vectors in 2- and 3-dimensional cases. Now, the previous lecture about scalar product, the most important result of the previous lecture was that if you have two vectors, A, let's say, consider it in 2-dimensional case, and vector B with coordinate representation A1, A2, and B1, B2, then their scalar product looks like this. So that's the most important result of the previous lecture. I also mentioned that scalar product should not really depend on the coordinates. It should depend on physical characteristics of vectors and their mutual position, their lengths and the angle between them. Well, but looking at the formula, we see that it looks like it depends on the coordinates. Well, it remains to be proven that if I change the coordinates in some nice way, so the matrix of the space is not changed, like lengths is preserved and the angle between vectors is preserved, like rotation, for instance, then the formula, though it does depend on the coordinate, but the result of this calculation with different coordinates would be exactly the same. So that remains to be shown, and probably I will have some problems related to this. Today, I would like to concentrate on different expression of the scalar product, not in the coordinate form, but in the form of these physical characteristics which I was talking about, which are unchangeable, so to speak, like lengths and angle between vectors. Well, let me give you the final result. Which I'm going to prove. Lengths of the first vector times lengths of the second, and the cosine of the angle between them. So that's something which is a final result which I will prove today. So if I will, and I hope I will, then it's reasonable to it's actually quite obvious here that no matter how I change coordinates, if this is a geometric interpretation of the scalar product, so no matter how I change the coordinates, the result should be exactly the same as this one, as long as coordinates are changed in a nice fashion, in orthogonal fashion. So the length remains the same, so we don't really scale the coordinate system, and the angle between the vectors remain the same. So that's my final result, and I'm going to prove it in two cases, two-dimensional case and three-dimensional case. By the way, I did not mention it in the three-dimensional case. There is a similar formula. If you have a third coordinate, A3 and B3, then the result would be here. That would be in three-dimensional case, right? So I didn't mention it in the lecture, but I decided to put it into the notes for the previous lecture. So if you're interested, it's exactly the same, basically, derivation with A3, B3 as in a two-dimensional case. But in case of a geometric interpretation, there is a significant complication in a three-dimensional case. So I will probably spend a little bit more time on this. Okay. Now, let's go to a two-dimensional case in geometric interpretation. All right. So this is easier because I can draw it on the board and everything is kind of obvious here. Let's say this is my vector A and this is my vector B. Now, these are coordinates, and I also would like to mention this is angle alpha and this is angle beta. All right? Now, I can express coordinates in terms of lengths and angles. How? Well, very easily. Let's say this length is A. Length of the vector A is A, and length of the vector B is B. So this is A, this is B. If you drop the perpendiculars here, 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 and here, basically you can express the coordinates in case of A, for instance. This is A1 and this is A2. For a B, this is B1 and this is B2. So I can use the hypotenuse of this right triangle to find A1 equals to A, the length of the hypotenuse, times cosine of alpha, and A2 is equal to A cosine of beta. B1 is equal to B cosine of beta, and B2 is equal to B cosine, sine. Sine. It's beta and this is alpha. Okay, now this is correct. Right. Alpha is for a vector, so it's a cosine and a sine of alpha. Beta is the angle of the b vector, so it's b cosine and b sine. Okay, fine. Now, since I have this expression, I can substitute this into my scalar product. And what will I have? Well, scalar product of a times b is equal to a1, b1. It's a times b times the cosine and cosine. So a, b, cosine alpha, cosine beta. And a2, b2 is ab sine alpha, sine beta. Well, if the angle between alpha and beta, between a and b, is phi, phi is equal to beta minus alpha or if you wish, beta is equal to alpha plus phi. Now, in this case, I can substitute this beta for these, and what I will have is AB, I will factor out AB, cosine alpha plus phi, plus sine alpha plus phi. So use square bracket. So that's my final expression. Now, this is what I'm thinking I would like to get. This is capital A, this is capital B, and this is a cosine of phi. This doesn't look like this one, right? So A and B I do have. But the cosine of phi is not exactly this. But maybe it will be exactly like that if I will transform it slightly. Let's just think about it. Now, cosine of sum of 2 is equal to cosine alpha, cosine beta minus sine alpha, sine, sorry, not beta, phi. Phi, right? So that's the cosine of alpha plus beta, alpha plus phi. Cosine minus sine. Now, plus sine alpha times sine alpha cosine phi, right? That's the formula. Sine cosine plus cosine sine. Equals. Well, let's just multiply. What do we have? AB cosine square alpha cosine phi minus cosine alpha sine alpha and sine phi plus sine square cosine alpha cosine phi plus sine cosine and sine phi, sine alpha cosine alpha and sine phi equals, well, first of all, this and this are the same with the opposite signs, right? Here, I can factor out cosine phi, and what do I have? Cosine square plus sine square. Now cosine plus sine square, cosine square plus sine square is 1, so I get AB and cosine phi, which is exactly what I wanted to get. So as you see, no matter how I position the coordinates, I can always express these coordinates in terms of lengths of the vectors and some angles, but after the manipulation, this particular formula basically gets rid of all these angles except one, angle between the vectors, which is phi. So this is a final formula for the same scalar product, but in a geometric fashion. Well, actually geometric plus trigonometric, but that's okay. So we are using geometric characteristics of vector, or if you want, physical characteristics, whatever, to express the scalar product. And that's very important. It depends only on the vectors, their lengths and their position in space, rather than how we choose the coordinates. Another thing which I wanted to present to you today is exactly the same problem in three-dimensional space. Well, in three-dimensional space, it will be a little bit more involved as far as the calculations are concerned. But the theory is exactly the same, and the formula will be exactly the same. It's still lengths times the cosine of an angle between these two vectors in three-dimensional space. So let's go for it and see if I will not make any mistakes on the way. In any case, I put all these calculations in the notes for this lecture, so basically it's really straightforward. I'll try not to lose my way around these three-dimensional coordinates. So it's three-dimensional coordinates, like this. Okay, we will do exactly the same. So first of all, I know that the scalar product is expressed as this formula using the coordinates. So I will choose certain physical or geometric characteristics of the two vectors. Obviously there are lengths and some angles. I need more angles in this particular case because it's a three-dimensional space. And I will use these physical characteristics of the vectors to express all the coordinates, put it in a formula, and see if whatever is necessary will be just reduced, and I will have only the product of these two lengths and the cosine of the angle between them. And I will, hopefully. So, first of all, how can I use this geometry of the three-dimensional space to express my coordinates in terms of lengths of the vectors? Okay, here it is. Here is the picture. Now, this is three-dimensional space. So we have x, y, and z coordinates. Now, x, y, imagine it to be horizontal, and z vertical up. All right? Now, if I have a vector, here is my vector A. Now, let's project it down onto the horizontal xy space. And this would be the projection of this point. So this is A1, A2, A3 coordinates. Now the projection here would have coordinates, obviously, A1, A2, 0, right? Now this would be A1, this would be A2. Now projection onto the Z will give me A3. And this point obviously would be 0, 0, A3. Now, let's have two angles. The angle number 1 would be from the x-axis to the projection on the xy plane. And let's call it alpha 1. This is a horizontal rotation from the x-axis to the projection of the a vector onto the plane, on the xy plane. Now, the second angle would be vertical, alpha 2, between this projection and the real vector. So I will use these two angles. Now remember, in a two-dimensional case, I only needed one angle from x-axis to my vector. Now in this case I need two. One from x-axis to the projection of the vector on the xy plane, and then another angle vertically up. This is called azimuth vector, and this is called altitude vector. So azimuth is within the horizontal plane, and altitude is within the vertical plane. Okay? So if the length of the vector A, original length, is A, now this is the projection, which means this is the right angle. So A is a hypotenuse, so the projection, length of the projection is equal to A times cosine alpha. A times cosine alpha, alpha 2. So I have this one. Now this is the right angle. So this is the hypotenuse. So A1 is equal to this times cosine of alpha 1. Hypotenuse, this is the catetus, the angle between them is alpha 1, so hypotenuse times the cosine of the alpha 1. So this is how my A1 coordinate is expressed. Now A2 is A cosine alpha 2, it's the same thing, but now I need this catetus, which is sine of alpha 1. And finally, A3 is equal to, it's this, which is the same as this, so it's the opposite catetus with hypotenuse A, and alpha 2 is angle. So it's A sine alpha 2. Obviously, with B, I will have exactly the same thing. I will have B, and angles would be beta 1 and beta 2. That's how I will use it, right? So I don't need this anymore, because everything else is just trigonometric manipulation. Okay, so my scalar product would look like A1 times B1, which is A B cosine alpha 2, cosine alpha 1, cosine beta 2, and cosine beta 1, plus AB. Now A2 is cosine alpha 2 sine alpha 1, and same thing would be for the vector B, and the third coordinate, the product of the third coordinates would be AB and 2 sines. Okay. So I wanted to prove that this is a times b times cosine of the angle between them. So this big expression, AB is obviously is factored out. Cosine, 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 cosine plus this, all together, they actually constitute the cosine of phi, where phi is an angle between these two vectors. Question is why? Okay, that's what I'm going to prove. I'm going to prove that this sum of these very complicated things is actually a cosine of the angle between these two vectors. And here is how. Let me go back to the drawing. Let's say this is vector A, and this is vector B. Let's consider this triangle. And I'm going to use, now this is angle phi between them. I'm going to use the law of cosines for this particular triangle. I know the length of this is B, this is A, and the length of this is something which I can obviously calculate based on knowing the coordinates. I know the coordinates of A, it's these. Coordinates of B are similar with the letter B and angle beta. So I can use just the formula between distance between 2 points, knowing their coordinates. Remember, the formula is the distance square is equal to A1 minus B1 square plus A2 minus B2 square plus A3 minus B3 square. Right? That's the formula for distance in Euclidean space between points A1, A2, A3 and B1, B2, B3. So I will use this as the third coordinate, and I also know that d square is supposed to be a square plus b square minus 2ab cosine phi. Now this is the law of cosines for this particular triangle. So equating these two things, I can see what will be cosine phi in terms of all these cosines of alpha 1 and alpha 2 and sines, etc., etc. So the equality between these two should give me the expression of cosine phi in terms of other angles, alpha 1, alpha 2, beta 1, and beta 2. So that's what I'm going to do. I'm going to calculate this and compare it with this, and that's how I will find cosine phi. And I will actually find that the cosine phi is equal to exactly this thing. I know this, right? So let's try. A1 minus B1 square. Okay. It's A1 square, which is A square cosine square alpha 2 and cosine square alpha 1 minus 2 A1 times B1. A1 times B1 would be AB cosine alpha 2 cosine alpha 1 cosine beta 2 and cosine beta 1, and plus b1 square, which is b square cosine square b beta 2 and cosine square beta 1. That's the first. Plus. Now, second one is a2 minus b2 square, which is a2 square minus 2a2 b2 plus b2 square, right? So a2 square is cosine square alpha sine square alpha 1 minus 2ab cosine alpha 2 sine alpha 1 cosine beta 2 sine beta 1 and plus b2 square, b square cosine square b2 sine square b1. And the third one, a3 square, which is this, minus 2ab sine alpha 2 sine beta 2 and plus b2 square, b3 square, which is b square sine square alpha, beta. Okay, now let's think about what this is. I don't need this anymore. All right, now how can we simplify it? Well, very easy actually. Look at this. A2 square cosine square alpha 2 times cosine square of alpha 1 plus sine square. So that's a square cosine square alpha 2, right? Now, if I will add this, a square cosine square and a square sine square would be just a square, right? So that's the result of this. Similarly, this would give me b square cosine square beta 2 times cosine square plus sine square, which is 1, right? Now if I will add this one to this, I will have b square cosine plus b square sine square. It will be just b square. Okay? And what do I have left? Minus 2ab times all this thing. This, and this. Cosine alpha 2, cosine alpha 1, cosine beta 2, cosine beta 1. Well, let me open the parentheses here. Now I will have only pluses. Cosine alpha 2, sine alpha 1, cosine beta 2, sine beta 1, plus, and the last one is sine alpha 2, sine beta 2. That's what I will have. That's the result of this. Now let's compare it with this one. A square plus b square, a square plus b square, minus 2ab cosine phi, and this is I have in square brackets. So whatever I have in the square brackets is actually a cosine phi, right? And look at this, it's exactly the same expression. Factor out ab, you will have exactly the same thing. Cosine alpha 2, cosine alpha 1, cosine beta, and cosine beta 1. Here cosine sine, and sine sine. So it's exactly the same thing. So this expression can be replaced here as ab times cosine phi. And that's the end of it, basically. So as you see, in a three-dimensional case, situation is exactly the same. I have product of the lengths of two vectors and the cosine of the angle between them. Again, it depends only on geometrical characteristics of the vectors, not on their coordinates. Well, that was actually everything I wanted to tell today. I wanted to present the case of geometric interpretation of the scalar product, and it is the product of their lengths times the cosine of the angle between them, independent on the coordinates. So as long as the coordinates are Euclidean, the vectors in space are positioned somehow the vector, and the angle between them. So no matter where is the coordinate system, how we move this couple of vectors around without changing their lengths and without changing the angle between them, their scalar product would be exactly the same. And that's the beauty of this particular thing. And if you remember, when we started in the previous lecture, I started with certain rules how it would be nice to have this particular scalar product adhere to certain properties, certain rules, as I was calling them. And one of the rules was independence on the coordinates. So it depends only on the internal characteristics or inner characteristics. Maybe that's why sometimes this scalar product is called inner product. Okay. That's it for today. I do recommend you to go through notes for this lecture. They are on unizor.com. Just to, to refresh that thing. It would be even better if you can just completely do it by yourself. Just have a piece of paper, draw some drawings, and try to derive, especially the three-dimensional case, which is a little bit more involved, and it needs certain spatial view. I do recommend you to do it just by yourself. That would be great, of course. So that's it for today. Thank you very much, and good luck. Hi, I'm Zor. Welcome to Unizor Education. I would like to continue talking about scalar product of two vectors in the context of the problems, actually. What I kind of presented to you in the last two lectures, which were purely theoretical, was the definition of the scalar product of two vectors. In particular, if you have representation as a tuple in the coordinate form, you have these two vectors, then the scalar product of these two vectors was derived in the following way. As this formula. Again, I derived basically this formula from certain common principles or rules which scalar product of two vectors would be great to have, so to speak. I mean, we invented these rules, and they seem to be quite natural, and so as a result of these rules, we derived this formula in the coordinate tuple representation of the vectors. I would like, as a problem actually, to go backwards. So, what if this formula is given to us? How can I demonstrate that all these reasonable and natural rules which we have established in the very beginning are actually held, are satisfied? So I will go through the same set of rules, and I will try to prove that this formula actually satisfies these rules. So even if we go probably more classical way of presenting this mathematical concept, okay, let's define the scalar product in this formula. Now let's check these properties, and the properties will be the rules which we're talking about. So let's go one by one with the same set of rules which I was using to derive the formula. Now let's actually derive the rules from the formula. Okay, now the first rule was independence on certain transformation of the coordinate space. The transformation which I was talking about was the one which did not change the matrix of the space, which means if the segment had certain lengths in the old coordinate system, then it would have exactly the same lengths in the new one. So the length is not changing. And the relative position of the vectors, like an angle between these two vectors, is not changed. So basically I'm talking about rotation of the coordinate system. Also the reflection relative to one of the axes is also of this type. It does not change the lengths, and that does not change the angle between vectors. Now, obviously, I'm not talking about any kind of a stretching or shrinking the coordinate system. So the unit length remains exactly the same. So actually, that's the most important property which we are talking about. Okay, so let's talk about rotation. That seems to be like a natural way of changing the coordinate system. And let's check that this particular formula is stable, so to speak, towards the location, towards the rotation. So after we rotate the coordinates, A1, A2, B1, and B2 will change, but the formula will result in exactly the same number. Now, to do this, to accomplish this, to demonstrate that the scalar product is actually invariant, which means it doesn't really change, invariant to rotation, let's just examine how the rotation actually changes the coordinates. So, let's say you had one particular coordinate system, x, y, and then you had a point somewhere which had certain coordinates. So the length of this is x, the length of this is y. Now let's say we change the coordinate system, we rotate it, and the new coordinate system would be this. This would be my new abscissa, which I will call u, and this would be my new ordinate system, ordinate axis, which is, let's say, v. Now, the coordinate of the same point, which used to be xy, now will be u, v. So, this segment is u, and this segment is v. I would like to express the lengths of these two segments, u and v, in terms of x and y, the coordinates in the old system, and an angle of the rotation. So this angle is, let's say, phi. Or I think I used alpha in my notes for this lecture, so let's just use alpha. So alpha is an angle of rotation. We have rotated this coordinate system this way. So the coordinates are changing. Let's try to express the new coordinates u and y in terms of the old x and y, and angle alpha. Now, what should we do? Well, let's put some letters so we will know what we're talking about. Okay, so B and C are projections of our point A onto the old axis. Now D and E, okay, we know that this is Y. So this point is E. And we know that this is X. Okay, it's clear. So, let me just do a couple of equations to derive the values of u and v in terms of x and y and angle alpha. All right, so let's think about it. I think I can say that AB, this piece, is equal to okay, we need the letter, let's say, M here. AM plus MB, right? Now, what is AB? AB is ordinate of the A in the old system, right? So it's Y. What is AM? Well, let's consider a triangle AMG. AM is a hypotenuse, AG is a catetus adjacent to the angle MAG, and angle is obviously equals to alpha, because there are two mutually perpendicular lines. So, in terms of catetus AG, which is an ordinate in the new system, which is v, I have to divide it by cosine of this angle to get the AM, right? So it's v over cosine of alpha. Okay, now what is MB? MB is a cachetus in the triangle ONB. OB is another cachetus. I know that OB is equal to, this is an abscissa of A in the old system, which is X. And this is also the same angle alpha, right? They're verticals. So MB is equal to X divided by tangent. No, multiplied by tangent, sorry. X multiplied by tangent alpha. Right? Now if I will multiply it by cosine, I will have y cosine alpha here. Tangent is sine over cosine, so the cosine will multiply and it will have only sine. And I will resolve it for v, so v is equal to minus x sine alpha plus y cosine alpha. That's my first equation. That's how v is expressed in terms of x and y, basically. So v we have already expressed. Now let's talk about u, this one. Okay, here's what I suggest. Let's just continue this line to point N, let's say. Now, I know that NA is equal to NC plus CA. NA is equal to NC plus CA, right? Now, what is NA? Well, consider triangle NAE, this one. This is again angle alpha. AE is abscissa of A in new coordinates, which is u. So the NA is a hypotenuse in this triangle, so it can be expressed with AE divided by cosine, which is u divided by cosine alpha. That's what NA is, right? And it's equal to NC. What's NC? NC is a cachetus in NCO. CO is another cachetus, and this angle again is alpha. So CO is equal to ordinate in the old system, which is y. So it's y times tangent alpha. And finally CA, CA is x coordinate, from which I multiply by cosine. U is equal to x cosine alpha plus y, tangent times cosine, that's sine. So that's my transformation of coordinates. Now, my question is, if instead of xy, I will use uv in this formulation and substitute using this particular transformation law each coordinate, will I have the same value? Well, let's just check it out. I should have, right? So if I replace x coordinate and y coordinate with u coordinate and v coordinate, so let's talk about new coordinate of the vector A. Vector A would be, so A1 is x, A2 is y. So my new coordinate is A1 cosine alpha plus A2 sine alpha. That's my abscissa in the new coordinate. And the ordinate, am I right? Yeah, I think I'm right. And the ordinate is minus A1 sine alpha plus A2 cosine alpha. So that's how my vector a1, a2 looks in the new coordinates which are rotated from the old one by angle alpha. Now, similarly with the b1 cosine alpha plus b2 sine alpha, comma, minus b1 sine alpha plus b2 cosine alpha. Okay? Now, my A times B scalar product would then be equal to, now the first coordinate times the first coordinate plus second times second. Okay, so we have four different members, because this is the sum of two, this is the sum of two. So it's A times A1 B1 cosine square alpha. Now this times this plus A1 B1 cosine alpha sine alpha. A1 A2 B1 sine alpha cosine alpha, and plus A2 B2 sine square alpha. Now I have to add to this the result of multiplication of these two. So it's plus A1 B1 sine square alpha minus A1 B2 sine alpha cosine alpha minus A2 B1 cosine alpha sine alpha plus A2 B2 cosine square alpha. So that's my result, right? Now, A1 B1 actually I made a mistake. This is B2. A1 B1, A1 B2, right, it's B2. I know it should reduce, that's why here, yes, A1 B2 cosine sine, A1 B2 sine cosine. So these two are out. One is plus, another is minus. Now this A2 B1 sine cosine, A2 B1 cosine sine, plus and minus, out. Now, A1 B1 cosine square and A1 B1 sine square, if I summarize them together, A1 B1 goes outside of the parentheses, and cosine square plus sine square is equal to 1. So these two sum up to A1 B1. Similarly, this one and this one, A2 B2 goes outside of the parentheses, and in the parentheses I have cosine square plus sine square, which is also 1. As you see, I got exactly the same as before, which proves that rotation of the coordinates changes the coordinates, but it does not change the scalar product. So scalar product is invariant. That's very important. Invariant relative to rotation and other transformations of the coordinates which do not change the metrics, lengths and angles of the system. Now, my proof actually heavily depended on some particular drawing where my point is in the first quadrant and my angle of rotation is just smaller than the angle to the point, etc. Now, you obviously understand that for every other kind of a variation of this picture, what if my point is not in the first quadrant, but let's say in the third quadrant, I will also be able to do exactly the same type of manipulations with a couple of triangles and expressing one through another. It's always exactly the same, so I don't really even bother with all these different cases. This is just an illustrative example, actually, that the system works. and it would work exactly the same way in any other mutual position of the points and vectors. So this was kind of a more difficult part of the proof, that all the rules we were talking about are actually preserved, because the rest of them are really trivial. So what was the second rule? Second rule was this. Multiplication by null vector is supposed to give the result equal to null. Zero, actually, right? So this is easy, because what is zero vector, null vector? Well, that's the vector which has zero length, right? Which means the coordinates are, it's just a point. It's a vector which is reduced to one particular point, which has no direction, and the length is equal to zero. Well, if you use this formula, where b1 is equal to 0 and b2 is equal to 0, obviously you will get 0. So the second rule is trivial. Now the third rule is that unit vector multiplied by itself should give the result of 1. Well, we are talking about unit vector multiplied scalarly, multiplied by itself, right? Which means that a1, a2 is exactly the same as b1, b2, right? So the formula would be, in this case, so the a would be, let's say, aa, and b would be aa. And what do I know? I know that the length of this vector aa is equal to 1, which means what? Which means a squared plus a squared is equal to 1, correct? Because what is the length of the vector? This is the hypotenuse, and abscissa and ogenet are two categories, right? So by Pythagorean theorem, the length of the vector square is equal to sum of the squares of the abscissa and ogenet. So if this length is equal to 1, then this should be the equality which I'm actually talking about. But now, what is the scalar product of a and b in this case? Well, it's a times a, right? Plus a times a, which is exactly a squared plus a squared. I know it's equal to 1, right? So that's how we prove this one. That's easy too. Next is associative law relative to multiplication by a constant. So k times vector a scalar product by b is equal to k times scalar product a times b. Well, this is again very trivial, because what is the multiplication of the vector by a constant in coordinate representation? Obviously, you remember that this is k1, ka1, ka2. That's the coordinates. Now, if you multiply this by the vector b, which is this, you will have ka1 times b1 plus ka2 times b2. Now, on the other hand, what is ab? ab is a1 b1 plus a2 b2, and if you multiply it by k, you get exactly the same thing as this. So that's trivial proof too. And the last is distributive law. I don't need this parenthesis, just by c equals ac plus bc, where c is c1, c2. All right? Now, how to prove that? Again, very easily. First of all, we know what is the sum of two vectors in coordinate form. This is sum of coordinates, right? Okay, so that's this vector. Now, if you multiply it by c, which is c1, c2, you will get c1 times a1 plus b1 plus c2 times A2 plus B2. Now, what is this? Well, AC is A1 C1 plus A2 C2. What is BC? Is B1 C1 plus B2 C2. Now this is exactly the same as this, because you can open the parentheses. These are just real numbers, right? So among numbers, the distributive law is working. So again, C1A1, which is this one, C1B1, which is this one, C2A2, which is this, and C2B2, which is this. It's exactly the same. So that proves actually that starting from the formula like this for scalar product, we can actually derive all the rules which we were talking about in the very beginning, from which in turn we derived our formula. So they are very much connected to each other. It's a natural kind of way of expressing these rules in a formula like this. Now the next lecture and the problems actually which I will present will be dedicated to exactly the same rules, but we would like to start from the geometric representation of the scalar product as the product of the lengths and the cosine of an angle between them, and again derive all these rules. But that will be the next lecture. Meanwhile, I do recommend you to go to unizor.com and go to this particular problem 1. This is called problem 1 in the scalar product topic, and try to do exactly the same as I did, especially the first problem related to rotation of the coordinates, because it's not really trivial. Anyway, that's it for today. Thanks very much, and good luck. Hi, I'm Zor. Welcome to Unizor Education. Talking about scalar product of the vectors. In the beginning, in the theoretical lectures, I have introduced certain rules or principles or axioms, if you wish, about the properties of the scalar product which it's supposed to be, which it's supposed to satisfy. Very natural rules like independence of the rotation of the system of coordinates, so it depends only on physical characteristics of vectors, their lengths and an angle between them. Commutative distributive law, multiplication by null vector or multiplication by unit vectors by themselves. So these rules were sufficient to come up with certain formulas for scalar product. Now, in case of, let's say, two-dimensional case, which is a little easier. So if you have two vectors with coordinates a1, a2, and b1, b2, then in the coordinate form, their scalar product, according to these rules, must actually be expressed as the formula like this in the coordinate form, or geometrically speaking, it's expressed as the lengths of one vector times the lengths of another vector times cosine of an angle between them. So we have two representations which were derived from these rules which I was talking about. Now, the previous lecture, which was like problems number 1, was about, okay, let's take the coordinate representation of the scalar product as given, and then derive all the rules which we were talking about, independence of the rotation, commutative distributive law, etc., etc. Now, I would like to do exactly the same with geometric representation. So let's consider that we have defined our scalar product as this: length times cosine of the angle between them. Can I derive all these very useful and nice properties which we were kind of put in the beginning as a foundation? Can I derive all these from the formula? So basically what I'm trying to do is to prove the necessity and sufficiency of the expressions in coordinate form or in geometric form for satisfaction of those rules. So rules and these formulas are in one-to-one correspondence, so to speak. They are necessary and sufficient condition for each other. So this lecture, which is basically a problem number 2 lecture, is proof that all these rules which we're talking about follow from the geometric expression of the scalar product. So let's just try to prove it. Okay, the rule number 1, the scalar product should not depend on transformations of the coordinate system which preserve the metric of the system, which means lengths of segments are not changed, and the angle between segments is not changed either. So it's like rotation, for instance, or reflection of the coordinate system relative to one of the axes, for instance. So, well, let's just look at this formula. It depends on the length of the vectors and the angle between them. And we just said that we are talking about transformations of the coordinate system which do not change it. So basically, from the problem itself, actually, from the conditions of the problem itself, this rule actually follows, because it depends only on the lengths and the angle. So no matter how we rotate the coordinate system or reflect it relative to some axis, the length of the vectors is not changed in these transformations, and the angle between them not changed either. And by the way, considering this is the cosine, which is an even function, it doesn't really matter we count an angle from A to B or from B to A, because all we are doing, we are changing the sign of the angle, and the sign, a change of the sign doesn't change the value of the cosine, because the cosine is an even function. So the rule number 1 is satisfied basically by definition of the transformation we're talking about. Now, rule number 2 is this. If I multiply a vector, any vector, by a null vector is the one which has length of 0, then I will get 0. Well, obviously, this b is a null vector, so the length of the b, again, by definition is 0, so this is the multiplication of length of the a, which is something, by 0, and by cosine of the angle, which doesn't really exist, and it doesn't really matter, because this is 0. So this is satisfied as well. Next is another simple case. If I will have 2 unit vectors, well, if I have 1 unit vector multiplied by itself, then the result is supposed to be 1. Well, again, it's very easy, because the length is equal to 1, this, and the cosine of the angle, if I'm talking about multiplication by itself, it means that I have 2 vectors which have directed in exactly the same direction, which means that the angle between them is 0, and the cosine of 0 is 1. So we have 1, 1, and 1, and that's why this product is equal to 1. So that's true too. Next is associative law. Okay, I have to prove that if I will multiply one of the vectors, which is a component of the scalar product, by a constant, then it would be the same as multiplication of this constant by scalar product of these 2 vectors. Well, that's very easy to see, because multiplication by a constant does not change the direction of the vector. It just makes it longer or shorter. It's stretching or shrinking, right? So the length is the only thing which is changed here. So what's the length of k times vector a? Well, the length is equal to this is by definition of the multiplication. Actually, I have to put absolute value here. This is a definition of the multiplication of the vector by a constant. We were talking about, when we were defining this, that the direction remains the same, and multiplication by constant is changing the length. The only little detail is that if the constant is negative, we change direction to an opposite. But again, it doesn't change the absolute value of the length, which remains to be exactly the same. Now, B is what it is. So on the left, I will have absolute value of k by a by b by cosine of phi. Now, speaking about cosine of phi, if k positive, then the direction between a and b remains exactly the same, so angle is exactly the same as it was before. Now, if direction is changed to the opposite, the angle, if this what used to be a and b, and now this is a times k, for k negative, then the angle is this one, right? So the angle is changed to the opposite. The direction is changed to the opposite, so the angle is changed to 180 if this is phi, so this is 180 minus phi, right? So as a result, my cosine is changing from the cosine of phi to cosine of 180 degree minus phi, which is minus cosine of phi, as we know from the trigonometry. So for positive constant k, the left side is equal to basically, I have to put, instead of this angle, I have to put 180 minus phi. And for positive, it will be the same phi. So let me just have two cases here. So this is for k greater or equal to 0. And for k less than 0, I have the same thing. And cosine, well, I can actually immediately write minus here and cosine of phi here. So that's what this part is. Now let's talk about this part. Well, this is always absolute length of A times length of B times cosine of phi. And we multiply by k. So for positive k, we have exactly the same, because the absolute value of k for positive k is k. For negative k, we have this, because this is exactly the same cosine of phi, right? So negative k would be equal to minus absolute value of k. So in both cases, positive k or negative k, we have exactly the same result. So that's why the left part is equal to the right part. And obviously, if I will multiply this vector, instead of a multiply b by k, it would also be exactly the same thing for exactly the same reasons. What I mean is this. It's equal to a, well, I don't really need this parenthesis, a times kb. That's exactly the same thing and exactly the same logic, but applied to the vector b should prove it. So that's about associative law relative to multiplication by a constant. Okay, and the last one is a little bit more involved, is distributive law. So distributive law is this. So this is a scalar product of sum of two vectors by the third one, And these are two scalar products of these two vectors. Now, when we were talking in the previous lecture about the same distributive law in coordinate form, it was actually very easy to prove, because the distributive law was actually between the vectors in the scalar product was reduced to distributive law among numbers. Geometrically, it's a little bit more involved. So let's do it differently. And again, it's not really for like really proving this thing. It's more of a mental exercise, because it's quite interesting if we can prove exactly the same thing, but using a completely different approach, a geometric approach, rather than algebra of coordinates. All right, so here is the drawing, and again, my proof will probably depend quite significantly on the drawing. However, even in differently positioned vectors, the proof would be exactly the same there. So I'll do it in this particular case. Let's put it this way. So let's say this is my angle B, my vector B. This is my vector A. So, and we need C, right? So, and this is C. These are my three vectors which are involved in this thing. So first I have to draw A plus B. So this is a parallelogram. That's how we draw the sum of two vectors, right? We take this one, attach it to the end of this one, or draw a parallelogram, doesn't really matter how we'll do it, and this is V equals to A plus B. Now, since we are talking about geometry, I need some angles, right? So let's say this is angle alpha. Angle between A and B would be beta. And I will also use this angle gamma between the sum of A and B relative to A. Okay. Now, let me just wipe out everything from here. We know all this, and I will use that space for something. All right, so what I'm going to do is I would like to, okay, let me just write again what I'm going to prove. All right. Now, to prove this, let me express the lengths of A and B in terms of the lengths of their sum and whatever the angles I have here. Now, I will use this triangle from here to here and to here, and use the law of sines to basically express the lengths of all these components. Now, by the way, this is beta, so this is 180 degree minus beta, right? Now, I will use the same letters, but without the bars on the top to express the lengths of these vectors, right? So talking about lengths only. So, V, which is this one, length of this vector, which is the sum of these two, divided by sine of this, V divided by sine of 180 minus beta. Now, sine of 180 minus something is the sine of that something, right? Again, we know this from trigonometry. Equals to, now this is A, and this angle is equal to this angle, which is equal to beta minus gamma, right? So it's equal to A divided by sine of beta minus gamma, and equals to B divided by, now this is B and this is gamma, so this is sine of gamma. So from this we can say that A is equal to V times sine of beta minus gamma divided by sine of beta. And B is equal to V times sine of gamma divided by sine of beta. Okay. Now, what do we have to prove actually? We have to prove that V times C times cosine of alpha plus gamma, right? V is the length of this, C is the length of this, and alpha plus gamma is the angle between them. We have to prove that this is equal to AC cosine of alpha, right? That's what this is. So VC and cosine alpha plus gamma is this one. V is the length of this, C is the length of this, and cosine of alpha plus gamma is their angle. AC is this, AC and cosine of alpha between them, and BC is BC cosine of BC. It's alpha plus beta. That's what we have to prove. So what I'm going to do, I will substitute this and this into A and B here, and I'll just try to prove this trigonometric equality. So we don't need this anymore. Again, I was saying that I would kind of depend on this particular drawing, but you understand that if any other composition, there will be a very similar considerations. So if I will substitute, instead of A and B, I will substitute this. What I will do, well, first of all, I can obviously reduce by C, and then V would be here and V would be here, so I can reduce by V as well. So I will retain only the trigonometric functions. So cosine of alpha plus gamma equals, instead of A, I will put this. So the cosine of alpha will remain. So it will be cosine of alpha times sine of beta minus gamma divided by sine beta. And here I will have cosine of alpha plus beta times sine gamma divided by sine beta. Or if I multiply by sine beta, I will get this. And this would be sine of beta, right? So that's what I would like to prove. Well, I still remember sine and cosine of the sum of a difference between two angles, so I will just open these parentheses and see what happens. Okay, sine of beta times cosine of sum. This is a cosine minus sine sine. Alright, so I will have cosine, and sine. Alright, so cosine of alpha, I will put it in alphabetical order. Then sine of beta, then cosine of gamma. Right? I don't need these parentheses. Too many parentheses. Minus, because this is a minus, sine, right? So I will have three sines. Sine alpha, sine beta, sine gamma. That's what I have to prove, that it's equal to this. All right, same thing, cosine alpha, sine cosine minus cosine sine, right? So it's sine beta cosine gamma minus the same cosine alpha, cosine beta sine gamma, plus this thing, cosine cosine minus sine sine, right? So it's cosine alpha cosine beta and sine gamma minus sine alpha sine beta sine gamma. Now, if I did not make mistakes, it should all be somehow equal. Well, let's think about it. This is equal to this. That's true. Cosine, sine, cosine. Cosine, sine, cosine. This is equal to this. And this, cosine, cosine, sine, cosine, cosine, sine, minus and plus, they nullify each other. Yeah, everything is fine. So basically this, a little bit more involved trigonometrically, proves that all the rules, including this one actually, the distributive law, are satisfied if we will give the definition of the scalar product only in geometric form. Length times cosine of the angle between them. So that actually completes this exercise of like proving of the equivalence of giving these 6 rules, which I was actually starting with, and derived the coordinate and geometric representation of the vectors. Equivalence of an opposite approach. We can define the coordinate as a coordinate representation of the scalar product in the beginning, and then we derive the rules as properties of this. Or if we define geometrically scalar product of 2 vectors, and then again we derived all the rules. So all these 3 logical systems, 6 rules, which seems to be quite natural, definition in the coordinate form and definition in the geometric form, they're all equivalent to each other. From any one I can derive any others. I do suggest you to go to unizor.com again to this particular lecture, to problems 2 it's called, and try to prove yourself exactly the same thing which I did here. I think it's a very useful exercise. And that probably would complete the theoretical part of the scalar product. There might be some other problems which I will add in the future, but basically this is the most important because it actually explains all the nuances of the definition of the scalar product and how the properties of this are. Well, that's it for today. Thank you very much and good luck.